Otherwise. Okay, yeah, sorry. I was going back to what we did this morning, and I'm just, yeah, it's not very useful actually that I do it here because I will cancel soon. Uh, let me just keep track of this in the old file because otherwise, so let me. Yeah, I just maybe just wanted to point out this fact, okay? But I will cancel. I will put in the old file. This is the file for the new lecture, so it's not very useful to put it here. So I just wanted to note that when you took to 2 here, so how does it look like? Well, you have a 2 here. That's easy. You have a 2 here, and then what you can write this. So remember that this is like we are in this torus, okay? And actually this is really a sum, okay? There's a finite set. And the right way to sum is that you consider the volume, the integral, discrete integral, let's say. And then we have this sum, and then here we have just the blocks in f point x squared, okay? That's what its norm is. And now you can work a bit in Fourier transform and you realize that this is essentially equivalent for all that matters to have really a kind of discrete Sobolev norm. Sorry, let me just write in this way. That is, this 2 to the power I looks like really the Laplace, the negative Laplace, so I can write in this way, okay? Some alpha power of the negative Laplacian when this is understood in Fourier space of f squared, okay? So something like this. Maybe I think we need homogeneous norm. Yeah, I think so. Okay, so it's something like this, and you can call this is like some Sobolev norm, okay, of order. Sorry, alpha over 2 of order alpha, okay, squared. Okay, so this norm, it's really when you work a bit the Fourier analysis involved here in this Hilbert space, then it's really that norm. Okay, so, and if you want, you define, okay, if you want, this is defined in this way. Okay, what is H alpha is really this norm. Okay, let me copy in the old file so that we have it. Okay, and then, so I was going on again in the material this morning, and we had this notion of the analysis of a product of two functions in Bezoar spaces, and then we understood, or I told you essentially, that everything is fine if the sum of regularity is positive. So now this you already know. If you know a bit of theory of distribution, you know that, I mean, you a priori distribution as defined only tests only regular function, but if you know something about the regularity, essentially you can have a bigger domain of definition. Okay, so distribution is a continuous linear functional in a bigger space and of function of limited regularity usually. For example, measures are really distribution defined for every continuous function, for example. Okay, like the delta. Okay, and then we started to renormalize, and we saw that when you take powers of the y's, which are the irregular objects, the random irregular objects, which enters into your equation, then you have to renormalize. Okay, the idea is that y square has no chance to exist because it's the square of something which I already told you it's very big if you look at it in a given point, but somehow y square minus some constant, which is diverging itself, so this will be like infinity minus infinity, but when you look in detail and you analyze this object using some probability theory, then you realize that this object actually has a well-defined limit as a distribution. So again, it's not well-defined in every point, but if you smooth it, if you integrate over a small region, then it will be well-defined. For the cube, it's more difficult. In 2 dimension will be the same also for the cube, but you have to subtract the different quantities, and how you determine what you have to subtract is not the matter for today's lecture. Okay, I don't think it's very important to understand the global picture. So you just know that you have to subtract something, and then it's well defined. In 3-dimension, it's trickier. It's not well defined as a function in time. That is, you cannot evaluate it at a given time. But again, if you look at it more weakly, like a distribution also in time, then it will be well defined. Okay, and this constant can be chosen to be the average of y. Okay, so you see, you subtract from the square its average, and then it's well defined. And for the cube, it's similar. Okay, you subtract always the same constant. Okay, the square of x, y. Okay, this is the covariance. Okay, these are Gaussian random variables, so all the relevant information is contained into the covariance. And then this is a key point conceptually. Okay, we allow ourselves to use a different constant in the initial potential. Okay, in particular, a constant which diverge as epsilon is going to 0, either logarithmically in 2-dimension or linearly in 1 over epsilon in 3-dimension. Okay. And this is conceptually what is called randomization. Okay, so the quantities which appear in the what is called Bayer theory, that is in your density, which you write at a given with a cutoff, has to diverge to compensate some irregularity, some divergence in the cube or in the nonlinear terms. Okay, and then we analyzed. So we were here. And we try to get uniform estimates. So the game will be the same. Okay, so let's play in 2-dimension. Okay, so let me get rid of all the rest here right now because I want to restart today's lecture. So let me get rid of something. Okay. So what happens in d equal 3? So in 2-dimension we have seen. So let me finish before what I was saying in 2-dimension. Then I will tell you something about this black box here. In 2-dimension, I was discussing the a priori estimate. So I don't put any weight because I don't need. I'm in a finite volume. The sums are fine. This integral, it's finite. Remember, you have epsilon. So this integral, no, that we define. So maybe I didn't say before, but somehow this integral to me is just, okay, so this integral is really a sum here. Okay, it's not a real integral because the space is discrete. So you really have a sum, and it really, I write it as an integral because somehow it's a large sum, but somehow you have a small factor in front. Okay, so essentially that. Okay, so and in 2-dimension, we did that. So we tested, and then we tried to analyze all these objects. And I remarked, so this is the key estimate. Okay, the only information you have on Z in this way of looking at the problem. There are other ways, and you have other information, but in this way is this the information you have. Okay, from this estimate. So you know somehow you can assume that Z is in H1. That Z has an L2 norm and an L4 norm, which are okay. Okay, you can use this information to estimate the right-hand side. And in 2-dimension, it works because I stated that somehow these objects are irregular, but remember in 2-dimension, alpha is just a very small negative number. Okay, so you have a very small, these objects are distribution, but of very regular distributions. Okay, they, in the sense that they have very small irregularity. And so you just need, so for this duality to make sense, if you want, you just need from Z a bit of regularity, and then it's fine. Okay. Again, everything just makes sense. Okay. What I'm claiming is that the estimate I get do not depend on epsilon, as epsilon is going to 0. Okay. And the key point is that the quantity you have here are really the quantity I claim to exist. Okay, these objects converge in these spaces, so this norm are finite actually. And then you get, so this is overall. Okay, so let me say, so in 2-dimension, so let me, so in 2D we have seen, okay, I keep it there because I will need it later. Okay, saying that we obtained the a priori estimate where the key point is that from this estimate, so this estimate implies, okay, let's see how we can use this estimate. Okay, we can use it in many ways. Okay, I already told you that there is a way to get stationary solution, okay, for that. So implies for stationary solutions zy, okay, that now you take the average, for example. So you take the average. So since it's stationary, the average of this disappears. So you just get average here. So essentially you get the average of that. So let me maybe write, so this disappear by stationarity. If it's not really stationary, you can do in other ways, okay? But you have this, and then you have a constant, and then you have the average of this Q, okay? And this is uniform. If you want, this is like depending on epsilon, okay? So this is maybe U epsilon. So let me point out that this depends on epsilon. But one, again, using some relatively elementary probability theory, one can prove. So that's the key point of this method. Okay, you try to, using the equation, you put you prove. So you see, you're using PD methods up to a certain point. You isolate all the difficulties inside a term which depend only on what you know very explicitly. Why? Since again, y is well known, and estimates are relatively easy. Okay, and relatively easy. Okay, it's a Gaussian. You have norms of a Gaussian, and you could estimate. Okay, for some power. Here, k is some power. Okay, so this is the method. Okay, so so this is via PDE methods, if you want, and then you have the probabilistic part. Okay, as a result, one obtain uniform estimates of the form. Now you reread this. This is 0, so you have that, but now you obtain these uniform estimates, and you should imagine in this way. Sorry, the integral, this is evaluated at any time, so you can evaluate even at time 0. I don't care, okay? So you have the supremum of this guy, it's finite. Now there is a question in the chat, so let me give a look. So the question is, are a priori bounds holds almost surely or without probability? This I took the average. Okay, so no, this holds almost surely. Okay, I mean in this bound holds point. Now the problem is this quantity finite almost surely or without probability? And this is finite almost surely. Okay, so the bounds, no probability here. Okay, this is they hold for all omega. Okay, if you want. I mean, there is no omega here actually. Okay, this is a PDE problem. Okay, I take samples. Okay, then of course, note that as a random variable, I could do this bound. The quantity could be plus infinity, but I don't care. So the random variable, it's finite almost surely. So then you go back into real world. You say, okay, this is a random variable, but with finite epsilon will be always finite. But so somehow it's not the point at this level. It's not even the point. Okay, so this is finite point for you just take trajectory which are actually very smooth, and this is a number, okay? So I don't think it's useful to remark here. So it's finite, surely, because y it's a finite, it's a continuous function, okay? So I don't want to put it here. So this estimate holds for, yeah, for all samples. Yeah, for all parts of y, okay, essentially, provided, since note that y of epsilon, it's y of epsilon, it's very well behaved function, okay? It's a continuous function from R times whatever, RTD. So these functions are very nice, okay? What we are trying to do, we don't have a problem to define our objects, okay? What we have a problem is to, so it is clear that Qt y is finite, okay? What we have a problem is, do we have uniform estimate, okay? The real problem is what happens when epsilon going to 0, okay? And okay, at this point, you take the averages, and now you can prove that uniformly, this average is finite, okay? And then this gives you uniform estimate on Z. Let's see if, okay, yeah, good. This gives you uniform estimate on Z. And now you think again, okay, what was my problem? Remember that, I don't remember how we called the measure. I need to check how we called the measure the last time. So the measure for the coupling, remember that we constructed Thursday this stationary coupling. So let me maybe recall, yeah, I call it gamma. Okay, so remember, so that Thursday, last week, we constructed the stationary coupling. Gamma, yeah, gamma, so that under gamma, yeah, such that under gamma, let me give a name to this stationary coupling. Let me call it P, okay, such that under P, the process Y and Z are stationary, and X plus and X equal Y plus Z is also stationary, and such that, of course, it's stationary because it's the sum xt as low nu epsilon m, okay, which is essentially, okay, we call m equal 1 today. Okay, so we had this property, okay, we constructed this coupling. If it's unique or not, I don't care, okay? There is no problem of uniqueness at this level, okay? I'm worried about estimates. So when you estimate something, you don't worry if it's unique, okay? Just anything as the solve the equation, for anything that solve the equation, I can do these computations, okay? So if it's enough that I have a stationary coupling, so actually I put it before, because yeah, so because I can use this stationary coupling under this stationary coupling. This estimate implies that, okay, so I use this coupling, and using this coupling, this does not depend on time. So when I take the derivative, it's 0. And I get just equality here. This is very important, okay? Because I already told you, if you have, if on the right hand side you have the initial condition z0, okay, if you integrate this inequality you get z0, then you don't know how to proceed. Okay, so now this is conceptually has been at some point the community realized that there were ways to go around this problem. Okay, so let me I will mention a paper of Albevero and Kuzuoka, which somehow it was the first one I read about, which somehow used this interesting idea that you can get rid of the initial condition, and somehow allowed Martina Osmanova and myself to think about how to do this in also to handle the infinite volume limit and write this paper. So proceed with the construction I'm trying to explain in this lecture. So this is very important that you can get rid of the initial condition here, okay? Because otherwise you don't know how to close your argument. But now the argument is closed, okay? On the right-hand side, you have only known quantities. On the left-hand side, you have only the quantities you care. And then again, okay, to estimate the right-hand side, you don't need to know anything more that you already know because it's Gaussian and you know everything. And so you have this estimate under the stationary coupling. And and you see you're estimating z and you want to know x, but you already know y. So that's giving you all the information you need, okay? Because somehow anything you want to know about x, you can construct with y and z, okay? So this estimate is a key point because from that one can derive tightness of the family nu epsilon, okay? Why I can derive, so that's what I wanted, okay? I want the tightness of this family of measure, okay? Why? Well, let's see. So indeed, take, for example, so now you have to be careful, okay? Tightness in which space, okay? And remember that x is the sum of y and z, and z it's regular somehow, okay? You know that you can control the H1 norm, the L2 norm, the L4 norm. You could even control higher norms, okay? The LP norm somehow if you work a bit more. But let's stop here. But y is not regular, okay? In the limit, you only converge in negative space, okay? So you have something which is negative and something which is okay, and you need to control x. Of course, you could control the pair. So indeed, consider the measure, okay? Okay, so let's call gamma the law of y0 and z0. So let me proceed in pairs, okay? We have, so for now, I want to control this law in the joint space. So I will take, so gamma is the law of the pair, so y and z. So let's call it psi, I don't know, I need to get and z, zeta for z, okay? So, and so in psi, which is y, I need to control some negative norm. So this you could control in C minus alpha, as I told you. Okay, so this would be finite. And for psi, you could control like the L2 norm. Let's say you control the H1 norm, and you can control other norms like L4, L2, and L4, for example. Okay, so you use this, you put it here. Maybe if you want to be happy, you can use square here. And this will be like the expectation of what you have here, essentially, okay? So of y0 and z0 and z0, okay? This is the law of that guy. And for that, you know, that this is bounded uniformly in epsilon. Sorry, this is in epsilon, okay? Under, yeah, let me let me put p epsilon because of course the dependence on epsilon is important. Okay. Yeah. Okay, so everything here still depend on epsilon because the law depend on epsilon. So I don't know if I put it again, but I think it's okay. Here I put it clearly. So maybe in the, yeah, I don't need to put because z depend on epsilon by time of the law. And here then you have that this family, now you have these bounds and this is uniform in epsilon. So here I could write supremum over epsilon. And now you have like supremum. Let me point out this is p epsilon. So this will be like equal supremum that. And we know that this is smaller or equal to some q of y epsilon. Okay, here you have this. Here you have this estimate. And that's done. Okay, so that's give you the tightness you want. Yeah, one has to be L4. Thanks. I just yeah, wrote too rapidly. Okay, so that's the idea. Okay, so this give tightness. I skipped some detail because everything was in tori with different lattice spacing, but you can embed in the same space. Okay, so this gives essentially tightness of gamma of epsilon. So you have tightness actually for the coupling, and then you project to nu in where you have tightness, in a space which contains C alpha for the first element, and then in the second element you see you have H1 intersect, okay, you have H1 intersect L4 intersect L2. Okay, L2 you don't need H2. Okay, let's put it there, whatever. You don't really need all this information. Sorry, actually no, you don't want to do that because of course you need to have tightness you need to use a slightly worser space. Okay, so here you can use 2, and here you have just to lose a bit on the, let's say something here. Okay, you have just to lose a bit on regularity, and then you have tightness. And I think if I write in this way, it's okay. Yeah, I think with this regularity, then you can recover the tightness in L4. I think it should be okay like this. Okay, some loss to guarantee the cursivity, see, the tightness, okay? The compactness, required compactness, okay? Otherwise, this functional does not have compact level sets. Okay, if you really look at it in the space where it says the object lives, then you don't have compactness there. Okay, so that's the idea. Okay, so projecting down to nu epsilon. Okay, so since you have tightness of the coupling, of course, the sum, taking sum of the two factors. Okay. So if you project this measure in the sum, then you get tightness. Okay, one get tightness of. Now you have to be careful where it's tight nu epsilon. Okay, and you have tightness in, for example, H minus 12. Okay, so this is like B22 minus 12. Okay, because you see, why is that? Well, you think, so what you have to do, well, I need to take a norm of this, a norm of, so this is new, so let's see what norm I need to take. Okay. Well, I said, okay, I want to obtain this as a projection of that measure. So you have psi and z. So this is the definition of y of this coupling, essentially. So, yeah, that's the coupling. Let me write it this way. And now you see one of two is not very nice, not regular, but very very much integrable. The other one is regular, but not very integrable. Okay, you have L4 or L2. You could opt for L4, but let's say I keep it easy, and I estimate this in this space. And then, of course, you can say, okay, this is smaller than the sum of the norms. Okay, you just estimate one and the other. And now you see that y, no? Okay, here you can replace with c because somehow it's like to go from L2 to L infinity. That's fine. Sorry, I need, yeah, I think it's enough like this. And here you can like go to H1, for example, if you want, okay? Because you have the control of the H1 norm here, okay? And actually, let's take this. I mean, the power is not very important here. You could, I could go with, I could go with just power 1, but just to be consistent with what I wrote. Okay, so you have this, and this is uniformly bounded. Okay, so which is uniform in epsilon. Okay, so this gives tightness in this space. Okay, so you can extract. Okay, so this gives the result in 2 dimensions. Okay, so we can extract accumulation, an accumulation point. Okay, a measure on this space. Okay? And now this is the two-dimensional term. Okay, you can state a theorem like there exists. Actually, okay, 2-dimension is not very interesting because there are many ways to obtain it, and actually you know that it's unique, but I will not, I'm not sure I'm able to prove it right now with this method, actually, that it's unique just from this point of view, but it has an explicit representation, so maybe it would be interesting to see if one can prove yeah, that there exists only one limiting point. So there exists an accumulation. So let me, so in particular, okay, we do not, okay, provided, let me write in this way. So provided we take, so you see that there is already beta, remember what we had done, okay? We took, okay, I didn't wrote it down. So beta was like something. Do I have it here? No, I don't have it here. So provided we take beta, how it was, so beta was minus 3 lambda, I don't remember, C epsilon, should be like this, plus beta prime for some constant. Beta prime inner and C epsilon equal, you see, this was very precise, okay, you could not. So this was something like this, then the family nu epsilon provided d equal to, and we take the family nu epsilon is tight, okay, in this space. Okay. Okay. So we have this theorem, this after first theorem of the after. So this is in 2 dimension, okay? Okay. Okay, let me make a small pause. So, okay, now I want to go, sorry. I want to go, what happens in 3? Now I want to discuss the most difficult situation, okay? Will take us all the afternoon and maybe all tomorrow, okay? So before going on, let me make a small pause. So this is the idea. Okay, one has to use somehow a bit of analysis to get better estimates, and somehow now we start to use this information about the regularity in the equation. Okay. Let me mention that yeah, in the post I discovered that there exists this interesting talk of Arthur Jaffe, which makes really a very nice theory, nice history, sorry, of the development in a mathematical theory of quantum fields. So somehow what I skip mostly, but essentially he was one of the major actors, and talks about the early years, and then when people were using Hilbert space method, and when people discovered Euclidean strategy and reflection positivity and so on, and where we stand now. It's actually quite funny because at the end, so it's mentioning stochastic methods very, very briefly in the end, and then of course he says higher and collaborators, okay, because of course I mean it's very vague. I had the impression it's very vague in his mind what's going on, and so he was remarking, he made an interesting remark because at some point he wrote a paper and he tried to analyze what happens to reflection positivity from the point of view of the stochastic dynamics, the Langevin dynamics, and then he did some computation and saw that actually, if you don't take the infinite time limit in the dynamics, imagine you start the dynamic at some initial condition, then you take the dynamics for some time, and he said in that paper, which you can find in the archive, I'm not sure, I don't know if it's been published, but if you find it, he found that the theory can never be reflection positive. Okay, but if you don't have reflection positivity at the beginning, okay, that was the point. So now the method we found, so our paper, the paper on which this lecture is based, somehow contradict a bit this paper of Jaffe, because somehow you can go around the problem. How you go around? Well, you start from the stationary measure, and this is not a problem. So I showed you that's not a problem. You start, then you run the dynamics, you even can find a stationary coupling, and then you do all the computation in a situation where you already know that reflection positivity holds, because I have already told you that it's very difficult to get back at the end. Okay, so in that paper, he was very doubtful that this stochastic approach would work because he could not see how to recover reflection positivity. But the real point is that really you don't have to give away reflection positivity at any point, okay, as I showed to you. And it's a discrete reflection positivity, but it's enough in the limit, okay? And we prove it in the paper with Martina. So it's a very interesting talk. I suggest, if you're interested in the history, to give a look. Also, try to motivate mathematicians to look more into these problems. Okay, as maybe some of you know that one of the Millennium problem is construction of a rigorous quantum field theory, mathematically rigorous quantum field theory in 4 dimensions. And I think the only candidate which seems to be available is Young-Mills theory. So one has to understand gauge theories to be able to work in 4 Euclidean dimensions. Okay, so that was a small pause. Let's see. So there is a question, sorry. Can you explain how white zero is taken care? Yeah, because I was yeah. So how you take care of white zero? Because it's you see it's inside here. Okay, white zero is one of these terms. Actually, I need to be let me be more precise, because everything here is computed at a given time. So let me. Yeah, I think here I wrote. Let me be precise so that we understand. And here you can compute everything at any given time. You have a stationary coupling. So this is really the things at time 0, okay? Because the coupling is stationary, so you don't care. and then you have y0. In particular, inside there is also y essentially. Okay, that's why you take care, you can take care. This is really part of that guy. Okay, modulo the power, but okay, maybe you have to, let me put in the definition, let me put 1 plus that, because so that it's clear that I can, yeah, I mean, you can take care of cost. Okay, let me write it like this. It's easier to than ever estimates. Okay, so it's already inside. Okay, okay, so note that. If I don't care about the constant, this is already inside. Okay, so this is like a smaller equal of q y0 if k large enough. Okay, but that was okay. Okay, so just, of course, you need to add, otherwise you add is not really a problem. Okay, good. Thanks for the question, I think. Okay, so let's go back to our discussion of 3-dimension. What we have to do. So 3-dimension is more difficult. Let us go back to the a priori estimates. Let me see if I want to go back to the a priori estimates. So how they look like. Okay, so let me. So again, okay, you do the same. You test the question. Actually, I don't think I have the question here. Do I have the question somewhere? Let me put back the question maybe, because it's useful to have the question around. Okay, so you test the question. So beta is always the same. Okay, we take beta from now on. We take beta in this form. Otherwise, we cannot. And we integrate in space now in 3-dimension. But okay, it's not very important to write it down precisely. But okay, let's do it. So the expression is the same, of course. Now, big problems. Okay, we have big problems. Okay, but now y2 has regularity. What regularity has? You compute, and it's this. Okay, and y3 even worse than minus 3 over 2 minus kappa. Okay, actually, let's say 3 kappa, here 2 kappa. Okay, because in some sense it's not defined at a given time. Okay, so these two terms are too irregular. Okay, for z we can opt only for h1 regularity from this estimate. Okay, so that's the problem. Okay, big problem. And that's okay. The technical term, that's a big problem. Okay. You see, these two terms are not under control. It means they can be very large or very negative, and then you don't have any estimate anymore. Okay, this term is still okay. Okay, the term y1z cube and even y1z are still okay, because y1 has a regularity. So these are the various regularity in 3-dimension. Okay, minus kappa. So these are the regularity you have to keep in mind. Okay, this is worse than minus 3 over 2. This is like minus 1. and this is minus 1/2. Okay, and here you have h1, so these terms are fine, but these two terms are not fine. Okay, so you cannot take limits in this and get something which does not depend on epsilon. So we have to do something, and this somehow this means that there are some problems. So we go back to the equation. So I go back to the equation. Okay, yeah, and write it more explicitly. So let me see if do I have another way to explain? Yeah, I think. Yeah, the pro more. Let's see what is the problem. So somehow the problem is that you cannot really get the estimates you want from here. So let's go back to the, sorry, here there is a dt which should not be around. How does it look like, this equation? So it was something like this. So let me just write formally. So it looks like plus, then you have m square minus Laplacian. I put on the other side. And then what I have in the right-hand side, I have minus 1/2, and then lambda y cube minus 1/2 or 3/2 over 2 lambda y squared z. Okay, before testing. Okay, and then you have other things. Okay, these are the terms which cause problem. And you see that this term does not depend. So this term, it's easy to get rid. It's the most complicated somehow, but it's easy. Actually, the most complicated to get rid of is that one. Okay, so this will be our true enemy somehow. The one which is easy to get rid of is this one, because I can get rid of it as we did for the Brownian motion. Okay, that is, you define the solution of this linear equation, and then you redefine what is your unknown. Okay, and that's somehow so from the theory you see from here. Okay, from the theory of parabolic equation, one see that z cannot be better, cannot have better regularity than 1/2 minus kappa. Okay, so somehow the idea is that this term has regularity minus 3 over 2 minus, okay, I put this 3 kappa, let's write it this way. Okay, and this somehow is a parabolic equation, so it gains only 2 degrees of regularity. So you just get this plus 2. Okay, so 2 plus that, which is 1/2 minus 3 kappa. Okay, which is positive, that's fine, but it cannot be, surely it cannot be H1. Okay, you don't have a 1 degree of regularity here available. Okay, you see, even if you don't have all these other terms and you try to solve this equation, you realize that this term has this regularity and you gain only 2. So you have really to change your point of view, because there is no chance that this H1 norm here stay finite. Okay, you see from explicit example, just ignoring all these other terms. Okay. So I want to, surely I can get rid of this term. Now let me, moreover, so you see this create a problem. Okay, in this case, we even have a worse problem for the term y squared 2. Okay, we'd have even worse regularity, because this is the product of something which is a product, something of regularity. So remember, y squared regularity minus 1 minus 2 kappa, and something of regularity, we said 1/2 minus 3 kappa. No, not good, okay? That's which is not positive. We do not sum up to a positive quantity. Not good, okay? So the first step is to isolate the most singular part. So the first step is to separate the problems in the product, okay, via a decomposition, okay? So we write, so the first step is, okay, let's rewrite this. You rewrite as a paraproduct, and what remains. So what remains, I use this notation for what remains. Where, okay, so this is just the sum of the other paraproduct and the resonant term, okay? So resonant term and other paraproduct. I think the notation looks meaningful. I hope it's meaningful to you, this kind of notation. Okay, by paraproduct estimates, one has. So now the paraproduct estimate, let's say what happens to this guy, okay? So this guy is of order so that this has regularity. Remember, paraproduct is essentially in the paraproduct estimate, this has positive regularity, so it does not enter, so it's only as a regularity of y2, that is minus 1 minus 2 kappa, and okay. Okay, so the n is well defined, and it is well defined. Okay, so the problem, the term containing the resonant product is, however, not well defined. Okay, so I have a problem. Okay, but at this point I have a nice decomposition. Okay, so remember that. So here we have z is to be made by this term, and then by something which depend on z again, and then something else. But you see, everything which depend on z, somehow it's linear. So okay, so just let me think a moment what I want to do here. Yeah, I think it's enough. Yeah, just give me a second. I need to think a moment what I want to do. Actually, I need to get rid of this term, but then I need to understand what's going on with this term also. Yeah, okay, here one has to work a bit harder. So the first thing to do, okay, so we have these two problems. Okay, so the first thing, so this is the key moment. Okay, so I need just to pay a moment attention, because I don't want, so we define, so let's get rid of this first of all. sorry, define a new stochastic object, and let's call it y, I don't know, with this notation, okay, y3 to be the solution of the equation. So now I want to get rid of this, and to get rid of it, it's easy. You just solve an equation where there is this term and you call it in this way. Okay, just okay. So this is now the only thing you have to understand is what can I can I solve it in a stationary way? I think in the paper we don't do that. Or maybe, yeah, no, I think we can do that. So let me, now I'm a bit perplexed. Take stationary. You prove that you can find a stationary solution of this equation. Okay, again, this is a very explicit functional of the Gaussian process. Why? And will be easy to analyze. In particular, one can show that uniformly in epsilon, it belongs to something like this, okay, like continuous function of time with values in C. I remember, okay, what we said. We said this is regularity minus 3/2, and then you gain 2 degrees of regularity when you solve a parabolic equation. Think about the heat equation. And this will become like 1/2 minus like 3 kappa, if you want, okay, on the torque. So this is the regularity of this object. Okay, so it's a positive, it's a function. Remember that everything depends on epsilon, okay? I don't write every time, but that's the point, okay? We have a finite epsilon, we want to send epsilon to 0, and we want to estimate which are uniform epsilon. So, okay, let me, and one will show that this belongs to this space uniformly in epsilon, okay, in the sense that the norm, in the sense, okay, that, for example, okay, so when I take the expectation of like the norm in a bounded time, let's say you do something like this, for example. In the infinite time, it grows, so you have to pay attention. In time, you cannot take the supremum over all time, but essentially you can do something like this, and when you take the supremum over epsilon, you get an infinite quantity, okay? And actually, you can take any power. Okay? Okay, for any kappa, t, whatever, okay, something like this. Okay, so you have very good control of this kind of thing. So let's not worry for this moment, just think that it's just a function in this space, okay, very nice, but it's not, for example, in H1, okay? And now one can define a new, so now I need a new letter, that's the difficulty in this business, let's call it H, to be Z minus this guy, okay? So you, okay, or you call Z, or you define things in, let me write in the other way so that it's clear what's going on. Okay, so I want to write Z as Y plus something else. What is something else? I call it H, okay? Where H, then solve the equation. So what is the equation now for H? Well, you go back and you have some equation like this. I don't write all the terms, but essentially looks like this. For H is is a new, now it will be the new unknown. Okay, you are just the change of variable because you want to get rid of this. And now here there is z, but z is this sum actually. Okay, and so let me write here, there will be a paraproduct. Let me write what I said. I decomposed the paraproduct into 3 terms. For example, okay, and then you have all the other terms, okay. And z of course you can leave it, but remember that z is defined just is this sum, okay. Okay, so we have a new equation. Okay, now the most irregular term is this one, and this irregularity of regularity. What is the regularity of this is -1 -2 kappa. So it's better than the previous equation, okay? But it's still not very nice somehow, this equation. Okay. Now, remember that z you have to imagine that you just write as a function of y and h, okay? There is no... Yeah. Sorry, yeah, I'm a bit... confused now what I needed to do. Yeah, let me pause. Yeah, so sorry, I'm back. And yeah, I was saying that somehow, yeah, one can continue in this direction, but then you realize that you still have to do some transformation to remove this irregular part. So it's better to proceed differently and to, yeah, start to introduce an intermediate objects first, which is defined yeah, I don't have enough names for things, so let me, I need so before defining h like this, so now define, now I need another letter. Somebody has to suggest me a letter. So y I used, z, x, w I don't want because it looks like Brownian motion, q I use for other things. It's getting hard. K, maybe not. Yeah, maybe not L. Let's call it L. Yeah, but L looks something. It's very hard to come up with right names for things. Y I used. Sorry. Start to use Greek letters then. Xi. I don't know if it's does not look fine. That looks like a noise. Omega. Like it's so difficult. That's the difficult part of the thing. Yeah, okay, let's call it H. I am not sure. And let me be a bit vague about initial conditions, because that's an issue later on and I don't want to discuss it right now. Maybe it just confuses. Let's see what I want to do. So this object has this regularity we saw. And okay, so I define this solution. Okay, so this is a linear equation. Okay, so this is a linear equation which can be solved and analyzed. Okay, so that's not a problem. Okay, you have a linear equation, and you have to trust me at this level that you can really solve this equation and analyze, and its solution lives in, and more or less you don't get much better. So where I have, yeah, you do in this space. Okay, does not look much different than this process, and lives also in this space. Okay, so that's all we need to know about this solution. Okay. Moreover, so now define. Yeah, that's a key point. Okay, so I think I don't want to. Yeah. Now we did like this. So now we define, but I change. Okay, so Z define that, give a name phi. I don't know phi. Let's call it phi. And you write like this. Okay, so this was H, and now you have phi. Okay, so phi is what remains. You have Z is H and phi. Okay, which solve. Now we can write what equation solve is solve phi. Okay, so that's the interesting part. So what happens to phi? So phi is the difference between Z and H. Okay, so if you think essentially the initial part of the equation is the same. Okay, so all the linear part is the same, and then there are other terms. Of course, this term disappeared because it's the same in Z in H, and the rest remains because it's linear. And so let me remove all this blah blah here. And let me copy the rest, because this equation will play a role. So I need really to have all the terms. So what I forgot here? Well, I forgot these linear terms and that. Okay, so I put them back so that we have the final equation looks like -1/2. Yeah, there is a 3/2 y. This was tested. This is Z. Okay, and then again -1/2 beta square y1 and z and z. Okay, it was like this. So that's the equation. Okay, so that's somehow an important point. So let's give a name. This is equation main, let's say phi. I don't give very meaningful names to equations, but okay, let's see. Okay, so this will be our new equation, okay? Because this equation now it's nice. I will show you that, okay? So this is the right equation to get a priori estimate for, okay? So let's test it with phi to get. So what happens if I test with phi? Okay, I get, now you start to see the pattern, okay? But somehow you get always the same thing, okay? You get an integral over the torus, the derivative, 1/2, and then you get like this quadratic form. Let me write in this way. So for the moment I leave it here because I would need. Then you get, sorry, I lost something. Yeah, there were also, Yeah, there were also, remember, a term like lambda over 2 and then z cube. Okay, of course, because it was on the other side you didn't, so but now I have there. And okay, this is a bit annoying written like this, but you should imagine that, so what is z? Well, z is h plus phi, and then you can write many things, but in particular, one of the things is just phi to the power 4, so I want it here. So this is like lambda over 2 with positive. And then you have a lot of things on the right-hand side. On the right-hand side, you have the integral, and you have all these terms tested with phi, so you will have something like this. And then you will have like also this term. Yeah, sorry, I just let's write down everything. So looks like this. Okay, and but I put on the other side phi, so it looks like actually like this. Okay, because I put on this side phi to the power 4. Okay, so you really have to write like this, and what is z is h plus phi. So let's remove z here. I don't know what is more useful to write, but sorry, let me check actually what I want. Yeah, I think it's fine like this. Okay, just let's keep it like this because it's not very helpful to, maybe I don't want even to write psi like this. Let me write it. This was, I mean t. Okay, everything is at a given time. It's not very useful either to write everything. Okay, so we have this. Okay, so that's the key point, the starting point for the estimates. Okay, so we have our good terms here. This is like the H1 estimate, then the L2, the L2 norm, the H1, the L4. And then on the right-hand side, we have a big mess. Okay, and now we have to cross fingers and check that all the terms in the right-hand side can be controlled with the left-hand side. Okay, so that's the goal. Okay, is this the case? And okay, looks a bit scary and problematic. There are many things which are not scary at all. This is nice. Okay, that's like a polynomial of order less than 4 in phi, because you see there is no fourth power of phi, so looks okay. H, I told you I know it very well. H is something, H you have to consider it to be something explicit and known very well. Okay, so actually I'm not sure if I want, okay, let's call it maybe bot. Okay, I don't know, I don't want to change its name, but it's something very, very explicit. Okay, maybe, yeah, let's do it like this. Let's call it like this blackboard to just say it's something I know it's at the same level of y. Okay, so it should be considered known. That's part of the, that's the somehow the technique here. Okay, so this is known and that's fine. Okay, that's not very scary. So the term t is not scary at all, since h is a nice function and it contains only powers less than 4 of phi. Okay, so it can be controlled via the L4 norm of phi. This term, okay, in the right hand side, the left hand side. Okay, so that's first part. Okay, so we should not be scared about worried about this term. That's fine. We know already it's like in two dimension. It's even easier than what happens in two dimension. Okay, works even easier. If you want, like this would be like in the infinite volume estimates. Okay, last week. That's very easy to control, okay? Just some Young inequality all around, everything is fine. Now, the worrisome terms are the first ones, okay? Because we know that y, so somehow the worrisome term, these are not worrisome. So let me just get rid of them. So let me get rid of this. So this term is also fine. So this term contains the integral, so don't forget, okay? So this term is also fine. So let's look, what is this? What is z? Z is this sum. So this term, it's really, let's rewrite it, okay? So what is this term? It's really, what is z? Well, it's h plus phi. So it's like this, okay? Is also fine. Since y is only minus 1/2 minus kappa irregular, and we have the H1 norm. Of phi. Okay, so phi it's regular, H1 is degree of regularity 1, so also the square of phi. Then this product, and you actually here we would have the cube, no, because but that's fine, okay. And it is at most cubic in phi. Okay, so crossing fingers should work, okay. So you need just a bit of the H1 norm, and with some work one can get a nice estimate. Okay, again, what is nice estimate? Is an estimate which only depend on the things you have on the right hand side. Now it's a bit tricky because note, however, that this term will contain products. So let me remark this. So there will be some strange product like this product, and then there will be the product like this times h square, okay? And these products are not well defined, okay? Because h is only of regularity 1/2 minus kappa, okay? So the regularity do not sum up to positive number. Okay, so these are a bit dangerous, okay? However, these terms can be analyzed with probabilistic estimates and shown to be okay, okay? More and no renormalization need to be well defined and not needing renormalization. Okay, so that's an important point. Okay, so they will not cause a problem for us. Okay, so they are well defined. Okay, one can assume, we will assume in the following that they have uniform estimates as epsilon going to 0 in G in C minus 1/2 minus. Of course, they cannot be more regular than y. Okay, so they belong to this space. Okay? And continuous function of time, let's say. So we have this, okay, like things like this. So these two terms are in this space. Again, okay, as above, okay. So this we don't care. So that's the message. I'm going back now to my estimate. So let's see. So I said this will be okay. This will be okay. This I don't. This there is not much to say about it. Okay, but right now I will keep it there because you will have another role very soon. Because unfortunately we will need another renormalization, And because the worrisome term are really the first two. So let me copy them. Okay. I'm worried about the terms. So the first two terms, okay? So let me carry around. So let me maybe remove that. So I have these two terms, okay? And you see that that's that critical. So let me just maybe put the 3 half minus in front, because, and even the lambda, because it's not playing a role now. It's really these two terms. Now we have to look at them carefully. And so you see, so what we see here, so y squared is regularity -1 minus something, okay? So just below -1. And phi, you can hope at most as regularity h1, okay? Because the only good term, I go back, the only good term you have is the Laplacian here, okay? So this gives you the h1 norm when you integrate by parts. Therefore, then here you don't have hope, okay? They are not in duality. Y square is not in duality with phi square, because phi square does not have enough regularity, okay? Since phi is not regular enough for y square. Okay, so that's the problem. So, and you see that we already have made that transformation. So the problem didn't get away. So I cannot get away from this problem. So there should be something going on. And what happens here, so here we use the following fact. And now the fact to be used is a lemma. So this is a commutator. So this is a lemma. We have, so now you look at this quadratic form. So, okay, let's take one of them. So you have F, G, and H. Okay, looks like this, like a trilinear form. Okay, so you have this trilinear form, you integrate in space. Okay, so you can see this is like the quadratic form associated to the operator of multiplication with the paraproduct, okay? But there is what you say, yeah, sorry, there is, so what I'm going to say is that you have a result here which somehow tells you that what is the adjoint in the L2 space, in this L2 space of the multiplication of the paraproduct, and the result is that the adjoint is the resonant product. Okay, so you can put this operation on the other term, provided you pay a price, and the price is that this is a trilinear function of FGH. So you define this as that, and now this is a trilinear form which is continuous in the norm. Okay, let me say is well defined and continuous. I don't want to introduce the real spaces, okay? So when the sum of the regularity of F, G, and H is positive. Essentially, that's the message, okay? And then you, for example, okay, then I give you just an example, but I think it's not example. You can estimate this with the norm of F in, for example, H alpha. So let's imagine, you see, this you have estimating all in, yeah, H alpha on H. Also, you can estimate in H gamma, and G is this object, so maybe I can estimate better in Chi alpha. Of course, you can choose the exponent whenever alpha plus beta plus gamma is positive. Okay, and so you say, okay, what's going on here? Well, the message you have to carry on is that somehow you have the right to replace, anytime you see this object, you have to replace with that object. and you pay a price, just another quantity. The difference is not exact, the replacement, but this quantity is well defined every time the sum of the three exponent is positive. Okay, so every time you multiply two things, you have to ensure that the sum of the exponent of the two exponent is positive, but here you have three exponent involved. Okay, so this is like a some kind of commutator. Okay, so that's a key point. It's not difficult to prove it, and looks strange, but somehow the idea is that you see this object essentially behave like G, and then if you remember the resonant product, what it says is that the resonant product looks at the same frequency for G and F. And here is the same, because somehow the frequency of this product is the frequency of G, then is like multiplied G, like if H was constant, okay, in this two inequality. Exactly what happens. So using this lemma, so let me maybe point out that this is this is an important lemma, because using this lemma, we have, so what this lemma can do for us is that, okay, let's look what we have here. We have this plus, sorry, let me write, so these two terms, okay, what happens here, so the sum of these two terms is correct what I'm saying? Should be, sorry, let me check. Let me check what I wanted to say. What's going on here? Okay. Yeah. Yeah, I think I still need. Yeah. Okay. I got it wrong. I needed to do. Yeah, I'm sorry. I was not really well prepared this afternoon. I really needed to do something else at some point, but I got it wrong. Okay, so somehow this lemma allows me to get rid of that. Okay, so it tells you that you can rewrite this as twice the paraproduct plus something else. So that's for sure. So you have T, you have YT, okay, something like this. But of course, it does not allow you to get rid of that, okay? Okay, so we still have a problem. We still have a problem here, because somehow in the right-hand side, you still have... no, I think I'm okay. Sorry, I think I'm okay. And overall, so this allows you to get rid of, you see, you got rid of the resonant product, but you still have the paraproduct, that somehow you still have a problem here, because this is not well defined, okay? We got rid of the resonant product, but the term is still dangerous. Okay, for the same reason, because you are not allowed, okay, this paraproduct is fine, but you're not allowed to multiply phi with that, okay? Okay, so at this point, I need to go back and look, how does it look like? So now in this, yeah, so somehow going back to the estimate, so a priori estimate, we focus on two terms. So on the left-hand side, there are a lot of things and that, okay? And on the right-hand side, we have that. Let me just check that I put the right coefficient there. So there is like this -3 because there were these two. So let's write it in this way. And then there are other things, okay? So the expression is like this, okay? And actually here, and now you see that, okay, I focus on them because somehow there is some hope that I can cancel them, okay? So the idea now, I think a part of this, of all this business is to, is to find ways to cancel bad terms like this one with good terms like that one. And somehow this one is the only one which can cancel this term, okay? Because you see, there is some, the idea is that actually phi is not regular enough to allow you to take the Laplacian or even one derivative of it, okay? And the reason is because there is this term on the right hand side. So, but you can look them together, okay? Putting them together. So, okay, let me say, I will and try to cancel the one in. So I cannot control this term. Okay, this term is out of control with the estimate provided by that. So I can cancel. I can try to cancel it using the term in the right hand side. Okay, using that in the left hand side. Okay, how you do it? So I think I will finish on this point. This is possible by taking. So I imagine, so how you cancel them? Well, you require that this object is equal to that, and then they cancel, no? So you want to require that phi as a special form. So is not a general function, but it looks like 3 of that, so maybe even -3 of that, plus something else. So let me call something else psi, okay? So let me define, okay, this is a definition for psi, okay? So by defining psi t to be this plus that, okay? And substituting, okay? Okay, now, yeah, sorry. Now, yeah, and substituting in the estimate. Yeah, now this is a definition, but if you don't do it right, it will not provide what you want. So somehow you have to complete the square, okay? We are completing above square. Because, okay, so I want to get rid of it, and I get rid of it by completing this square, and I have to do it right, which I didn't possibly here, because when you complete the square, maybe you need not. So you see, this is quadratic. This you have to think as linear, and then you will have, like, to complete the square, you will have to add twice that. Yeah, sorry, I'm thinking what I want to say here. You need to add, twice that, but so let me see Do somebody see how to complete this square? Yeah, let me check the coefficient. Yeah, but the coefficient here do not coincide. So, yeah. So sorry. Let me. What I want really to do is, is to do that. Of that. Let's see what's happened. Okay, let's see. I will do the computation so that we check. So what happens if you substitute here? That, okay? So I want to substitute. So I have, this will become the integral of what? So psi is that. Let's see which is the right coefficient. And then you have the Laplacian. And then you have again the same quantity. Okay, so it's something like this. How does it look like? Well, okay, you have the expression where you have psi, that's easy. Okay, so you have the square, then you have twice. So you have -6. And then an expression which is symmetric, okay? And you see that on one side you have a psi, and on the other side you have the Laplacian of that. So you have exactly what you were looking for, but you see that the coefficient is wrong. So maybe here you need 3/2. So now it's getting the right coefficient. Because of course it's the square. So now you have 3 here, which match this 3 exactly. But of course you have a price to pay, and then you have 9/4 of looks something which looks like the integral. Sorry if I confused you at some point, but I think now it's fine. Okay, you have this operator cancel that. These are elliptic operator. Okay, so no problem. And you get something like this. Maybe let's put the other parentheses to be clear. So this is like some square. Actually, you can put the operator in the middle because it's really like a quadratic form. Okay, you can integrate by parts. This operator. Symmetric. Put on the other side. So you can just write this as like this. Okay. So you see that here it generates this object which is exactly, no, I got it wrong. I know. No, I think it's fine. Sorry. It's like this, but you see on the other side you have phi, and so you have to put back phi. So this is why I always got confused by this computation. And now I want to put back phi, so I need to put phi. I can put phi here, but then I have to minus 3/9/2, and so this becomes minus, okay? Because then the quantity is the same. Okay, so finally I managed to do this computation. So you see that, so these terms which appear in the estimate generates another term like that, but with the psi, not the phi, and then this term, which cancel exactly that one, and an additional term, okay? So now our a priori estimate reads, so let me write down because it's important. There will be some more randomization to do. So let me just write down so I summarize what I'm doing. So I go back. I take the estimate again. So this is, I think this is an important point. So now here I can put back the psi here. Let me just check that, yeah. Here it's fine, okay? You need to keep the fit into shoes somehow. This cancel, you see this term now cancel that one, but cancel also the resonant product, okay? So it leaves only the other product here, but of course we have to pay a price, and the price to pay is that we have to, maybe I forgot a lambda, so we have to add this additional term. So we add this additional term on the redundancy. Sorry, I forgot a lambda because term on the right hand side were coming with a lambda. You see that in the equation you have, yeah, you have lambda. So I think here you have to add also lambda. And then there is lambdas everywhere around. So let me just correct so that we have the right estimate. Let me put it on the new line. And I think now we are fine. And also the time is up. But we are in good shape now. Okay, so now we have this new expression. So we have that, and I think we are good to go. Okay. So this is the expression we will need to use to continue to estimate things. Okay, so the right hand side is still good, and then here we have. So here there is still some problem. Okay, but why there is a problem? Well, look at this. This is regularity -1 because essentially it's the regularity of that. Every time you see a paraproduct, you can just ignore if a positive regularity, which you hope so because you have these terms. You can ignore it and you have just y square. Okay, so this is like y square, which is regularity -1. Then you gain 2 degree of regularity here. So it has regularity just below 1, but then you multiply via y square. Okay, so this is not regular enough to be controlled. Here it's good. Okay, this paraproduct is not a problem because you expect psi. I hope it's not a problem. So psi has positive regularity, and surely the sum of the regularity is bigger than 1. So you can get rid of this thing and have a finite paraproduct. And here it's fine. We already said. Yeah, remember that Z is H. Actually, here it's not fine. Sorry, I wrote something wrong. That's not good. Sorry, I go back because I said something which is not good. So these terms are not fine at all. Yeah, so sorry, I was wrong. So these terms actually are not fine. So one of them is actually containing, so this is H1, H, phi. So phi is fine because phi will have, so let's look back. Sorry, yeah, so the point is that yeah, so now this discussion is premature at this level, okay? What is the problem? The problem is that, you see, I was obliged, let me go back, I was obliged here to do this transformation, okay? So now phi is the sum of this term and psi. And the only thing that remains is the norm of psi. So let me go, so let me, with psi, so phi, now phi, you have to read it back, okay? So somehow everything depend, so phi is just minus that plus psi, okay? Something like this. Okay, with psi t in H1, but this shows, however, that the regularity of phi is only like 1 minus, you see, this is regularity 1 minus 1 minus 2 kappa, and this gain 2. So this is 1 minus 2 kappa, okay? So somehow this object has regularity 1 minus 2 kappa coming from essentially this guy. Okay, so you can ignore the paraproduct when you do this computation, just to understand the regularity of. Okay, yeah, so let me stop here because on Thursday I will restart from here and I will resume this last computation, which maybe were a bit messy. So the point is we have to understand still if everything is fine, and it will be fine, but somehow there will be some renormalization to be done. So this is the last step, is really the conceptual difficulty of the three-dimensional problem, because you have to do this additional renormalization. So somehow on Thursday we will discuss the additional renormalization needed to give a meaning, a well-defined, more well-defined limit to the quantities. So this is require a bit of time, but somehow the quantity which pose a problem is this one, because it does not have the regularity, and there is another quantity, and the other quantity somehow is hidden. Is hidden where? It's hidden here. So the other quantity is like the integral of phi, and then there were y1h. So let me so here there will be h square and then h z t. Okay, so these two quantities are not very good because you see this irregularity just above 1/2 and this is below 1/2. Okay, so this, yeah, I'm a bit sorry, yeah, and yeah, okay, so yeah, this term which will be like, yeah, it's this one, okay, because this will looks like, remember what is y at first order is like y cube, is y cube squared. So there will be another y cube here. So these terms are not regular enough. So one would have to consider like something like this. Plus other terms eventually. Okay, but somehow this term require renormalization. Okay, which, yeah, okay, which should be, yeah, which diverges as epsilon going to 0. So I will explain this part, okay? That's this more subtle renormalization. So now these terms are not well defined in the limit. And one has to subtract something, and what you have to subtract is really the reason why I still keep around the parameter bit, okay? So somehow here, one should make a suitable choice of beta prime in order to, this will be taken into account by a suitable choice of beta prime. After, okay, as soon as we have good estimate, yeah, this will solve the epsilon 0 limit, and then we will discuss how to put together the epsilon 0 and m infinity, the techniques to handle epsilon 0 and m infinity limits. Okay, so let me